Welcome back to the next part for the second part of the algorithm running time complexity. My name is QD Azani and you guys watching my channel Coriowood. Okay, so in the last part we've seen the worst case, the average case, which is sometime, and we said that the best case is bogus. There is no such thing as a best case, so you guys should not, if you have a best case, it means it's cheating. Our algorithm has learned some way and cheated, so it's never happens. If it happens, it's a bogus. And we have amortized complexity, and the best way to explain is average time taken per operation if you do many operations. And we've seen this, that as we say time of input size n. So you guys remember this one. All right, so we're gonna go on the second part, and if you guys see here, we have a graph, and we have a different color graph, and you guys gonna see the O of 1 and O log n and O square root n, and say O of n. It says O of n log n, and it says O of n square, and that's cubic. The last two, this is the exponential and this is factorial. So we don't put this one, you never see these things, these two last guy here, because they're one of the worst. It costs you guys a lot, so you guys never see this exponential. And as I said in the previous part, in the last part, the part 1, that's exponential ones, you guys don't want this one. Say we said that the polynomial one's okay, but exponential ones is worse. You guys don't want this one, these two. So there is factorials as well. Sometimes you guys gonna see the factorials here, and we don't want this one. So we have here x, which is the size of the problem, and we have here y, which is how long it takes. So we have x and y, and the first one you guys gonna see, this O of 1 is a constant time. Such algorithms run in time independent of input size. And if you guys remember, in the previous we said algorithmic time running time complexity is a measure of how long it takes for an algorithm to complete when there is a change in size of the input to the algorithm. And usually that's the number of elements n, rather than actually measure the time taken, which varies for on the programming language. And we said the processor speed, architecture, what sort of computer that is, Windows, or is that Mac, or what year is that manufacturers, and all of them is a factor. And we consider the time to be the number of basic operations that the algorithm has to take. We always consider the time, which is this guys here, the time, whatever the time take is, we consider the time all the time. This gives us a metric independent on the user's computer that we can use to rate one algorithm against another when solving a problem. And we said we always interested in the worst case, which is upper bound. We have a big O, we have a little o, we have a big omega, and we have big theta. So the big O is upper bound, O function of n, and we say big omega, we're going to see in the next video, big omega is the lower bound, and big theta is the exact bound of the upper and lower. And big O is one of the most common ones. That's what we put it here. That's a big O. That's a big O. You guys going to see that's a big O of 1, big O of log n. We have a little o as well. There we have a big omega, and then we have a big theta. And so big O is upper bound, big omega is a lower bound, and big theta, that's exact bound. That's included the both upper bound and lower bound. So you guys see it here, says that's the first one, that's the best. Whatever you guys going to see here, this guy here, this is the best. So constant time, which is a constant time, and O log n is the best. You guys gonna see here, and they're okay, and they here is okay. So if you guys want to put, you guys can put a green, whatever here is a green all the way here, and this is, you guys kind of put a, say if you want to put 3 colors, this is gonna be red, it's gonna be it's gonna be yellow, and here you guys gonna put red here. So, and here you guys can put a dark red. So you guys don't even put this one here for the time, because this one takes a long time. This exponential is useless. This factorial is useless as well. We don't want this one. We don't want the exponential. We don't want the factorial, but this one's okay. The cubic one's okay, and this quadratic one's okay too. N log n's okay. This is linear. Linear is okay. So we're gonna first, we see here, that's O of 1, And we say that O of 1 is a constant time. Such algorithm is run in time independent of input size. And the example, if you guys go in Java, say the first thing you guys going to put a hello world, or you go C++, and you guys going to see out hello world, or hello Yazdani, or hello whatever hello, and you guys, as soon as you guys put the enter, it's going to process and it's going to go boom on the screen. That's how long text is a matter of milliseconds. So this is the best time. So O of 1, which is a constant time, is the best time. It runs at the in time independence of input size. So that's the first one, is O of 1, which is a constant time. The second part is log n. You guys going to see this log n. The bed be put it with O of log n is logarithmic time. So this guy here, you're going to see this is okay too. Algorithms in this class often work by repeatedly reducing a problem to a subproblem, a fixed fraction of the size. So O of log n is a time complexity of the running time complexity, where the number of operations grows with the logarithms of the size of the input. So whenever the number of operation grows, whatever, if you guys put the double the size, and the operation grows on this double. Every time the size of the input doubles, the complexity increases by a constant amount. And the example of, see what you guys going to see, the while loop. You guys can put a 0 to I, and we'll put I less than n, and print hello, and print whatever, and that's how it's going to take. You guys can put this one on binary search algorithm. You guys can put Fibonacci numbers, and you can put it on divide and conquer. O to the of square root of n, a basic algorithm for integer factorization, goes through the number from 2 to square root of n to find the prime factors of n. You guys don't see this much here, but that's, you guys can use it for prime numbers. You're going to see that if the numbers is a square root over prime. So if you want to check the primality of a number, you only need to look for factors which are less than or equal to the square root of the given number. So square root of n is when we trying to find say the primality of any number. So we can see is prime method for the loop starts iteration from the 2, or only go to the square root of n. Say if you want to find a prime number, you can see this is, but this is okay because this sits underneath the linear time complexity, and this is between the of log n, and you guys going to see that's a constant time of log n. I didn't put this one here because I put a linear time, is because we don't see this one of square root of n. You guys don't see that much, but for if you guys looking for like want to find a prime number between the numbers, you guys can use this one. So if you guys gonna go on Java and says public static boolean, and if want to find a prime, and we're gonna say boolean if the prime, and then we're gonna use the math of square root n, and you guys gonna find the first one, which is if it's 2, and then it's gonna be 5, and then it's going to be 7, whatever the number is going to be true, and that amount of time it takes, you guys can use this one of square root of n. Okay, and the next one is going to be linear time. Such algorithms generally perform constant time processing for each input time. So the linear time is when the algorithm grows at the rate proportional to the number of elements n. And for a loop, if you guys want to put a run a loop, and for I in range, and you guys want to range say hello, and you guys going to see it takes from 1 to 10. So if you guys from 1 to 10, or from 1 to whatever the number, and you guys going to print 1 2 3, or you guys want to run any loop, so all your loops going to take a linear time. So this is a linear time. Or if you guys want to go say want to find out the range from 1 to 100 or something like that, so you guys can use this one. That's much how much time the linear time takes. The next one is going to be the n log n. Yeah, you guys can put it n log n time. So of n log n, divide and conquer algorithms belongs to this class and work by decomposing the original problem into smaller subproblem, solving this and then combining the results. So that's quadratic time. We're going to put it for later on. So n log n, that's a divide and conquer algorithms, belongs to this class. So this guy here, n log n, if you guys look in here, this one holds n and log n. So this is a combination of n of the linear time. If you guys look in here, linear time and log n. So this n log n, and you guys can put it, because here we said the logarithmic time also divide and conquer. This guy is here also n log n divide and conquer algorithm belongs to this class, because as I said, divide and conquer is like America goes to Iraq and divides the population into Shia, Sunni, Kurds, and then they want to make sure that they don't like each other. Then they rule one of them, because they divide the problem into sub problems. So because one problem you guys can't deal with it, and with the sub problems you guys deal with it. Sorry for the politics, but that's reality. That's how America applies the algorithms to the population to rule. So this one, if you guys hear the divide and conquer algorithms, because we're going to divide the problem into many sub problems, and then we're going to solve that one by one, and that algorithm belongs to this class. So this is the O of n log n, and this is also known, this n log n also known as the best complexity that you can sort an arbitrary collection of elements in. So to demonstrate in your coding, you guys can go for a nested loop. So you guys go for I in such and such, and you guys gonna put assign 0, and then you guys can put your say while, or you guys can put another flowing loops in that one, so you can print whatever you guys want. So the merge sort, heap sort, and quick sort belongs to this algorithm as well. And because we've got a divide and conquer, but you guys keep in mind that the algorithm is time complexity, running time complexity of n log n complexity, the merge sort, heap sort, and the quick sort belongs to this guy here. So the next one here, you guys of n to the power of 2, you guys are going to see that's how we're going to read quadratic time. Most such algorithms spend constant time processing all pairs of input time. We're going to see the cubic time right now again. So the quadratic time complexity is proportional to the square of the number of n elements of n. This is the best form of complexity to have, especially when n grows large. So as when the n grows large, this becomes bad and bad. So that's what we guys, we don't like it, because this comes into the, as I said, this one comes into the red zone. This algorithm here, even n log n is okay, but these guys here, they are not okay, because they're gonna comes into red zone. So the example of this one is when you guys gonna do, say, nested for loop. So you guys gonna do for I is 0, I is less than such and such, and then you guys gonna run your another loop, which is gonna be another loop for this one. That's how it's gonna take, because it's gonna take a long time. If you're running the nested for loop, is a 2 times the repetition of the algorithms of the quadratic time running time complexity. Repeating an algorithms or performing it twice does not change the complexity. So keep in mind that whatever, if you guys repeat the algorithm twice, it does not change the time, the complexity of this time. This guy here, we read it as O of n to the power of 3. We read it as cubic time, because that's cubic. This one is quadratic, and that's cubic, because we have a 3 on top, or to the power of 3. Most such algorithms spend linear time processing all pairs of input items. So the quadratic time running time complexity is rarely seen in a single software algorithm, but it's a combination of many multiple algorithms to solve a problem. Say we have a for loop, then we have a nested for loop, and we have a 3 for loop. So it's a for loop within for loop within for loop. That's how this guy is, the quadratic running time. So it takes a long time. We can keep on going forever explaining poor and poorer of complexities. So we can go to the n to the square root of 4. So we get n to the power of 4 or n to the power of 5, whatever. We can go deeper and deeper, but it's going to take the more time it takes. And this time complexity is very rarely seen in the software market, industry market. You guys very rarely seen that the software takes this running time complexity, the cubic time. So this guy is here. That's I didn't put it here, because this guy is exponential time. You guys don't see the exponential time, and you guys don't see the factorial time, but these 2 times exist, and you guys don't see rarely this one. So 1, there is a 2, 3, you guys don't see that much, but they exist. So for the sake of completing so I just wanted to show you guys all of these running time complexities in here in my graph. So that's how I'm explaining it to you guys, but you guys rarely see this exponential time and this factorial time. So exponential time is, that's how it's going to return, just 2 to the power of n, exponential time is always greater than any polynomial time. So the example of this exponential time is the implementation of when you guys gonna calculate the Fibonacci sequence with the dynamic programming. So when you guys go in Python and you guys gonna when you go and do the Fibonacci series, number series, then you guys gonna, that's how long it's gonna take the exponential time. And the last one, last but not least, you guys gonna see the factorial time is written like that, or then there is exclamation mark is written as factorial running time complexity. It's a very rare and hugely expensive complexity class as a permutation algorithm. This is, you guys rarely see this one, the factorial one, because this is gonna cost you guys a lot, and this is very expensive, and that's why you guys don't see this much in the graph. But for the sake of complexity, I thought I'd just better put it here so you guys be aware. So running from here, you guys gonna see the green goes here, and you guys gonna see the yellow goes here and stops here. So this area is yellow, and this area is gonna be red. This area, this from quadratic and cubic all the way to exponential and factorial, and it's going to be red, and this is no go zone. So this guy is here, especially this guy, and this guy is going to be no go zone. That's why you don't see that in a lot in many algorithm books. So you guys don't see the factorial one, and you guys don't see the exponential one, but this one, the rest you can see. Whatever you can see in normally in algorithm books or algorithm classes, whatever, you guys going to see the constant time, you guys going to see the linear time, n log n time, quadratic time, and cubic time. So they are one of the most used whatever you guys want to do inside algorithm. You guys going to see this time running time complexities. But if you don't do that, if you guys go and do the exponential time, or you guys going to do the factorial time, then you guys don't see that in but they exist. They are all running time complexity. So that's how I put it here. And you guys going to see this is the last guy here, and the last guy takes a lot, and it's going to cost, it's very heavy, and it's very costly, and it guys going to cost you a lot time wise. And if you look at, this is the best, and this is the second best, and this one is the third best, fourth best. And as you guys moving this direction, they're becoming into the red zone, and all the way to this very red zone or no-go zone. And the next one beside this one, there was another one is called exotic time. Exotic time is O of n dot n. So you guys gonna put a O, then you guys gonna open your parentheses, gonna n multiply n factorial. So that one's gonna be exotic time. So that exotic time is very expensive, and there's no need for me to put it here, the exotic time. So there's no need for me, the last one I put it here, the factorial one. So the factorial one should be enough. And you guys, I said you guys in most of the algorithm charts, you guys going from here, you guys going to see the constant time, then logarithmic time, then you guys going to see the linear, then n log n, and then you guys going to see the quadratic, then you guys going to see the cubic, but you guys not going to see this one, the exponential, and you guys not going to see the factorial. So this one you guys not going to see, but it's there, it exists. So that's how you guys going to see this, all this running time algorithm. And now you guys know that the algorithm, but we can take a lot of approach to design algorithms. Then in the future videos we're going to see the greedy algorithm, we're going to see the divide and conquer algorithm, then you're going to see the brute force algorithms, and dynamic programming as well. Why we use a graph? If you want to check the algorithm is to best suit our problem, what sort of problem we have and how long it takes, and according to our graph we can determine if we can do the algorithm, which way, which approach or methods we're going to take. And to make our job easier, we use the big O notation, because big O is force running time complexity, and that's how we're going to see that one. But this, keep in mind, this because we are here at the green zone, this is a constant time. So this is there's no growth rate for this one. This is like I said, you say hello world or something, it runs, and this guy is here, it's linear time, so the time grows like that. Like if any guy is going to see this one, it means it's a linear. Okay, and this guy, two guys here, as I said, this guy is the worst one, so you guys never see this one inside the algorithms. But you guys going to see when this guy comes inside the red zone. So this guys, as we present the example, they are coming into red zone. So that's how you guys gonna interpret your graph. Alright guys, that's it for this video. If you have any question or comment, leave in the comment box. Otherwise, I'll see you guys in the next video, and bye.